less than 1.2. Again, for like, what, the 5th day? Something like that. As I said, it's a really big lesson. But this is really big stuff that we will use all throughout. This is stuff that continues on for us. Continues into calculus, for that matter, too. Okay, first topic of the day. Even and odd functions. And when we talk about even or odd functions, that relates to symmetry. I'm trying to think if you guys have really talked about even and odd functions in algebra. I'm not feeling like you have. Okay? So, let's go with a little bit of definitions, first of all. Functions that are considered even. Okay, so a function can be even, odd, or neither. So functions that are considered even. There are two ways to tell if a function is even. And we're going to look at both of these ways. Because there are certain times that one is more, more usable than the other. So one way to tell if a function is even is if it has symmetry across the y-axis. And in order to see symmetry across the y-axis, you need to be able to look at a graph, right? So symmetric across the y-axis means what? Y-axis, it's the same on both sides, right? It can fold over on both sides. So that's one way. That's your graphic way. Algebraically, if a function is even, f of negative x is equal to f of x, which is the original function. So what that's saying is, if you put in a negative for x, and it then turns back into the original function, it's even. Okay, so that's even. We'll look at some examples of that. Odd. Functions that are considered odd, first of all, they have origin symmetry. Okay, origin symmetry is they're symmetric across the origin being the point 0, 0. I'll show you an example along the way. When I see origin symmetry, I see a graph that it's kind of like diagonal quadrants, right? But I think of it as it reflects twice. So it's like it reflects across the x, and then you take that and reflect it across the y. Or it could be the other way around. You could reflect it across the y, then take that and reflect it across the x. So it kind of does a double reflection there, and that will end up being origin symmetry. Algebraically, if a function is odd, then f of negative x equals negative f of x. So this one is you put the negative in for the x, you get the same as if you would just multiply the whole function by a negative. So we will check that out. So we have 3 examples here. The examples are told whether the functions are even, odd, or neither. Also determine their symmetry, which goes right along with it. Obviously, graphing is going to be the easiest way, right? For that reason, I want to look algebraic first. So in order to check whether a function is even or odd algebraically, you need to find things like f of negative x and negative f of x. So my suggestion is always to start off finding negative f of x. No, not negative f of x. F of negative x. Sorry, I'll get it straight here in a moment. So let's do that on this one. Let's find what f of negative x is. So if f of x is x squared minus 3, what's it mean when I put negative x in every place I see an x? Well, so in this one it's x raised to the second, right? So what am I raising to the second instead this time? And negative x raised to the second minus 3. What is negative x? Negative x raised to the second? Yeah, it's positive x squared. And then minus 3 is still minus 3. What do you know about that function and what it just equaled? X squared, it just equaled x squared minus 3, and what was the original? X squared minus 3. So what just happened? F of x is equal to f of negative x. What does that tell me in terms of symmetry? Or in terms of even and odd? Okay. If f of x, the original, equals the same when you plug in the negative, it's going to have some symmetry across the y-axis, and it's going to be even. So right there, without any other work, I know that this is an even function. Now, if you graph this, what's the picture going to look like? What? A parabola. X squared minus 3 is what? A parabola that is down 3. Is that symmetric across the y-axis? Yeah. And again, that visual's not enough for you. There's x squared minus 3. Now, could you have just looked at the graph and known this was even? Yes, you can. Again, there's times I want to be able to do the algebra. There's times I can just use the graphic. And this is where I want you to be able to see both. So, just for the visual in your notes, I was going to sketch the graph. And that right there is helping me understand that this is even, and thus, I'm going to write a note in here, symmetric across y-axis. So there's an example of an even function. B. Okay, if we're going to start algebraically, what am I going to suggest you start by doing? Okay, let's start g of negative x. And the reason I start g of negative x, whether it's even, whether it's odd, I need it both ways, right? So g of negative x, I'm plugging in the negative every place I see an x. So it's negative x raised to the second minus 2 times negative x minus 2. Okay, do the math. Negative x raised to the second becomes positive x squared again. Minus 2 and minus x becomes plus 2x minus 2. What do you know about the x squared plus 2x minus 2? It's not the same as the original. So what can I say right now that I know for sure? This function is not even, right? I won't go as far as saying that it's odd yet, because I don't have any proof that it's odd. And keep in mind, there is a neither option. Okay, so right now, all I've proven is that based on the original, this is not even. Okay, so that one. Those guys were not equal. So what do I need to find next? Not graph yet. We need to find negative g of x, because if it's odd, that one's going to be necessary. So now, let's find negative g of x. Did you understand what negative g of x means? I'm going to take the whole function and multiply by a negative. So if I write it in terms of this, it's the negative of x squared minus 2x minus 2. Or if you go ahead and do the math, distribute the negative, yes? So if I distribute the negative, it's negative x squared plus 2x plus 2. Is negative g of x the same as g of negative x? Yeah. Did this come up the same as what we had already come up with? No. So what do I know now? Okay. That one specifically right there tells me that it is not odd. If it's not even and it's not odd, then that means it is neither. Okay. If you graph it, you will find that there's just not a whole lot of symmetry going on anywhere. X squared minus 2x minus 2. Obviously, I didn't really leave room to graph this on the paper, but It's a parabola, right? So there's symmetry, but based on where this parabola is located, is it symmetric on the y? No. Is there, and again, I haven't shown you a good example of it yet, but do you see a diagonal symmetry where certain quadrants are the same as other quadrants? And no. So this is a neither. So I want you to see a picture of what a neither looks like. Okay, ready to try C? Algebraically, what do I find first? H of negative x. So that means we put in a negative every place we see an x. So it's going to be the negative x raised to the third over 4 minus negative x raised to the second. What's this come up to be? What is negative x raised to the third? That is negative x to the third over 4 minus, what is negative x raised to the second? Positive x to the second. So my denominator is still 4 minus x to the second, but my numerator is negative x cubed. Is there any way that that can be equivalent to my original? No. If I had all my signs different or something, and it's a fraction, we could talk. But in this case, so what do I know right now? It's not even right now. Okay. So what do I need to find once we know it's not even? So negative h of x. Now, we talked about this as multiplying the whole function by a negative, right? Which in terms of a fraction just means multiplying the front of the fraction by a negative. So let me clarify. This is not multiplying the entire top and the entire bottom by a negative. Because then if you multiply top and bottom by a negative, negative divided by negative is a positive, so you're really multiplying by a positive. So, when I multiply this by a negative, are these going to be the same? Or maybe I should say, can they be written the same? I have a choice with this negative. Do I want to multiply it to the top, or do I want to multiply it to the bottom? Well, what's it going to make it look the same? You multiply it to the top. So negative x cubed over 4 minus x squared. So what do we know? This is odd. Now, graphically wise, okay, Mallory's already graphed it. She says it looks weird. But what is it going to be? It's going to be symmetric across the origin. So let's see what that looks like. Basically, there's a bunch of asymptotes happening here. Okay, guys. I know because of my denominator, I have asymptotes happening at x equals 2 and x equals negative 2. We'll talk more about that later. Now, I said symmetric across the origin, right? The best way I can explain it. Pick one quadrant and then do a double reflection with it. Reflect it across the x and then the y, or the y and then the x. And it will always land up looking like itself. So, for instance, if I just take this quadrant 1 up here, it's just that right half of that cubic. Looks like right half of a parabola. If I flip it down, then it's down here. If I flip it over here, well, then it's overlapping that right there. Or I can take this quadrant down here. I could flip it up and then flip it over. It looks like that. I could flip it over, then flip it up. The idea is, you see what I mean by that kind of diagonal? Okay. when we reflect across the origin. Another way to think about it, trying to think of another way. I think the other way is if you make both coordinates negative. Is that what it is? I think if you flip across the origin. So, are you guys seeing it? If you want a visual in your notes, I don't know, there's a little spot up here. I was going to put a little sketch. It's not going to be great, but I have that, what I'll call a cubic in the middle. We'll talk about that more next lesson. And then we have these pieces of the graph doing this thing over here. Okay? So, that's my best attempt at a sketch of the graph. Okay, even and odd. I would encourage you to practice right now, trying the algebraic and then using the graphic to confirm. Not saying you couldn't do just graphic, but there is value in being able to understand the algebraic here. Questions on the symmetry, and the evens and odds. Okay, let's talk asymptotes. We talked asymptotes a little in the previous part of the lesson, didn't we? Yeah, we talked asymptotes when we talked about removable and non-removable discontinuities, right? You guys remember which is which? Removable, non-removable? Which one's a whole, which one's an asymptote? Okay, good. Non-removable is an asymptote, removable is a whole. So we're looking at those non-removable discontinuities, asymptotes. So vertical asymptotes. This is old news. This is me refreshing your brain. Vertical asymptotes are any place that make the denominator equal to 0. Okay, denominator equal to 0. That's how you find a vertical asymptote. And so to find the vertical asymptote, we will set the denominator equal to 0. Now, remember, if that denominator then cancels with the numerator, okay, that's a whole instead of an asymptote, but this is how we find it. Horizontal asymptotes. We had this in Algebra 2, guys. You had when it came quiz test time, I know there was a paper that I have rules on for you. Don't count on that this year, but you did have that last year. So horizontal asymptotes is all about powers. If the biggest power is on top, then there are no horizontal asymptotes. So biggest power on top means if I have x cubed plus 1 over x squared plus 2x. What do we mean biggest power is on top? X to the third is bigger than x squared, right? That's an example of no horizontal asymptotes. Now, if the biggest power is on bottom, then y equals 0 is the horizontal asymptote. For example, if I have x squared plus 2x over x cubed plus 1, where's my bigger power? X to the third is on bottom, that's the bigger power. So that's a horizontal asymptote of y equals 0. What line is y equals 0? X-axis, right? Y equals 0 is that x-axis. And so your horizontal asymptote when the bigger power is on bottom is always the x-axis. And then, the third option, if the powers match, top and bottom. So if the biggest powers match, then you use the coefficients of the biggest powers. Okay? So, for example, if you have the equation y equals 3x cubed over 4x cubed plus 1. What do you notice in that one? The biggest powers are both x to the third. So my biggest powers match. I have x to the third on top, x to the third on bottom. Take the coefficients. What do I mean coefficients? Yeah, the 3 and 4, the numbers in front of them. And so in that case, my asymptote would be y equals 3/4, which just is that horizontal line through 3/4. Over here, y equals 0. I don't know if you want to write it in or not, but that is the x-axis. Okay? So those are your horizontal asymptotes. Okay, let's put this to work. Make sure you're following along, please. This example asks us to determine any horizontal or vertical asymptotes of the graph of y equals x over x squared minus x minus 2. I think we're also going to sketch the graph. I need to review. I forget what it is that I asked you to do in homework here. Okay. So, what do you guys want to start with? Vertical or horizontal here? Vertical? Okay. We start with vertical asymptotes. How do we find vertical asymptotes? Okay, set the denominator equals 0. My current denominator is x squared minus x minus 2. That's technically what I'm setting equal to 0. What do you need to do with that denominator, though? Factor, okay? Look for factors because, if it will factor, that will tell you your asymptotes real easily. So, 2 parentheses. X squared breaks up into x and x. What multiplies to be negative 2 and adds to be negative 1? Negative 2, positive 1. What do I do with both of those pieces? Set them equal to 0. X minus 2 equals 0. X plus 1 equals 0. Solve these each for 0, and what do we get? Okay, x equals 2, x equals negative 1. Those are my vertical asymptotes. Okay. Horizontal asymptotes, what's the rule? What do we need to look at? The biggest powers. Okay. Well, my only power on top, right, is x. My largest power on bottom is x to the second. So where is the biggest power? On bottom, because x squared has a bigger power than x to the first. What is the rule when the biggest power is on bottom? Y equals 0. So I know that I have a horizontal asymptote of y equals 0. Okay. Before I move on to the bottom section, one of the things that we're going to start doing is we're going to start looking at graphs a little bit. I'm going to do this without a calculator, and then we can kind of confirm with a calculator. But I want to kind of show you some of the things we know about this graph and what it's going to look like. So let me just over here in this open area, draw myself a horizontal set of axes, or a horizontal vertical axis. If I'm trying to graph this without my calculator, what can I already go ahead and put on my graph? What do we know? Yeah, do I know some asymptotes? Yeah. I know there's a vertical asymptote at 2. How do we sketch in a vertical asymptote? Dotted line. That shows me my graph will never cross or touch that right there. I also have a vertical asymptote at -1. Same thing. My graph will never touch or cross. What else do I know? There is a horizontal asymptote at y equals 0, which is the x-axis. Now, horizontal asymptotes are a little different. Technically, my graph will occasionally cross that, but only in the middle. My graph will never cross horizontal asymptotes as they go off to positive and negative infinity. Now, because my function here is positive, okay, what that tells me is that my graph is going to start on the positive side here of the x-axis. Well, as my graph is running along this horizontal axis, what's it going to do? What's it going to have to do when it gets here to this vertical axis? It's going to have to turn and go where? Up. So right there is the first part of my axis. Now I'm trying to remember how much of this you guys have to know. But another rule I can tell you is that when we get to an asymptote, unless you have a different reason, your sign changes. So right here, my graph was positive, yes? My graph is now going to change to negative. I'm trying to think, how did I show this in the past? Okay, so what I know right here is that my graph's going to start down here. That's right. I'm just trying to show you the asymptotes more than anything. Now, something we'll talk about later is the fact that intercept-wise, if you put in 0 for x, this does come out to be 0. So this does go through the point 0, 0. Since it goes through the point 0, 0, there's an example of where it's crossing through. And again, you don't have to be able to sketch these by hand in homework. That's what I was just remembering. But it goes through there, and notice it runs along the other asymptote. Okay, again, this one ended up positive. What did I say about asymptotes? They will change, and so now it's going to start down here negative. Now this one, as we go off to infinity, where's my graph going to go? It's going to follow this horizontal asymptote off to the end. Okay. If I graph this real quick, you'll notice similarities here. Okay. Can you see the asymptotes on the graph? Okay, that's a big thing, is I want you guys being able to identify and understand it. Okay, there's an asymptote there. I understand there's an asymptote there because I saw it on the graph. Okay, trying to decide here. Do I want to try and throw this last bit in here? Let's look at this last bit. We may or may not get through it because we only have a couple minutes left, don't we? Okay. In behavior, when I was talking about that horizontal asymptote up there, okay, I mentioned in behavior. I don't know if you guys caught it or not, but it's what my graph is doing as we move infinitely off to the left and infinitely off to the right. So it's following along that horizontal asymptote. Because notice, My horizontal asymptote is y equals 0. Where is this graph approaching? Y equals 0. Where is it approaching over here? Y equals 0. So in behavior is what's happening when we approach the far left. So the far left being negative infinity and the far right being positive infinity. If there's a horizontal asymptote for the function, it'll be approaching that number. If the graph is going to infinity or negative infinity, then we'll approach that value. Now, what I'm going to say, when it says determine the end behavior of the function, I want you to think horizontal asymptotes. That is going to be the main thing that's going to help you here. So as we look at A, work with me guys, y equals 3x over x squared plus 1. Biggest power's on the bottom, so what's that mean? Y equals 0. Because as we look, it's 3x over x squared is what matters there, isn't it? So biggest power on bottom, it's going to be y equals 0. Another way to think about this, guys, is an x cancels, and this ends up being 3 over x. You have that whole, or that asymptote, at x equals 0. Okay, look at B. What do you know there for horizontal asymptote? Why? Yeah, if we look at the powers are the same, 3x squared and x squared. And here's another one to think about, guys. What happens? Those x squareds can essentially cancel, and you have 3 over 1 or 3. So we have a horizontal asymptote, y equals 3. What about this last one? Okay, there's no what? Okay, because we have bigger power on top, that's what I was afraid of. I'll have to talk about this one tomorrow. There's no horizontal asymptote, but there is a diagonal asymptote. And so we'll finish talking about that one tomorrow. Go ahead and do your homework. The only section you should really run into problems will be the last section, I think. The rest of it should be fine. Yeah. And the last section I'd have to help you with anyway. So go ahead and do the homework for tomorrow. We'll check it. Page 95, 48 through 66 even.
Morning, Shane. How are you doing? Morning, good, right?